Okay. Does anyone have any questions from last time? So I've got the speaker set up there. It allows me with the mask to just speak at a conversational level. So my mask doesn't get so hot. So, but feel free to adjust the volume. If you can't sleep, turn it down. If you can't hear, please turn it up. So you can't tell when I'm smiling now, can you? So you guys never know if I'm actually being, I'll tell you, I'm pretty sarcastic, so take anything I say with a grain of salt, maybe, since you can't see my facial expressions. So I do have, so last time, this first chapter is kind of an introductory chapter. I mean, we did some stuff last time with talking about the wave equation, and really the class is not going to kind of be taught at that level where you have to know. It is pretty heavy. There's a lot of math in this class, a lot of Calc 3, which is usually everyone's least favorite calculus class with contour integrals, surface integrals, that type of thing. And we certainly will get into that. It requires a lot of visualization in 3 dimensions, which is not easy for a lot of students either. But I want to continue, kind of wrap up chapter 1 today. We will be working a lot with sinusoids, sinusoidal signals, at least later in the semester when we get back to waves. And it has a section where he has a review of phasors. Okay. So a phasor is nothing more than a complex number that represents a sinusoidal signal. I know that you saw these actually starting back in circuits 1 and EE320. That's been a year or 2 years for all of you. And then certainly in 215, you worked with phasors throughout the course. So this is the sinusoidal waveform. Here I've got a V, so the 10 is it represents a voltage. So in circuits, you worked with DC signals first, then you transitioned up to more complex signals. But the second signal you worked with was actually a sinusoidal signal. For 2 reasons. They're common. They're commonly used in industry as either test signals or the signal coming out of the wall is a sinusoidal signal. But then also because of Fourier transforms. You can use Fourier transforms to represent kind of any signal as a sum of sinusoids. So, but the corresponding phasor just includes, so it's not nearly as cool as the Star Trek phasor, but it's just a complex number to us. And it represents the amplitude and phase of the corresponding time domain signal. So it's pretty easy to go back and forth between the time domain representation and the phasor representation. Notice it doesn't include omega here, the actual frequency. So you have to know that in order to work problems with phasors, in order to go back to the time domain representation, you have to know the frequency at which the source is operating. Okay. So I want to review a little on complex numbers. I highly encourage you to spend some time with your calculator. Review. Hopefully you got pretty good at using your calculator and evaluating complex numbers back in circuits 2. Okay. I can't tell you how to operate your calculator. I do have a couple of tutorials up on my website. I'll link them. I'll put links to them on today's lecture on the website. On like the TI calculators, the TI-83, the 85, 86, 89. I think maybe there's another calculator or 2 that I know about, just with some tips. In particular, you have to be careful with the TI-83, which I think a lot of you have because that's what they recommend in calculus. There's a little trick you have to use for that. I don't like the TI-83. It's not really convenient to use for complex numbers. It's got a bug in it, but you can use it. Okay, you just have to be careful when you use it. But it talks about that a little bit in this tutorial on the website. So there's a couple of different representations that we use for complex numbers, and we use the letter J in electrical engineering to represent the square root of -1, the imaginary unit, because we use I so much for current already, right? So typically in physics and math, they'll use I instead of J, but we use J. And this is what's called the rectangular representation, or the Cartesian representation of a complex number. So we can represent the point. It's got two components, what we call the real and imaginary components. So we can represent the complex point, or this complex number, as a point on a plane, where the horizontal axis is what we call the real axis, the vertical axis is the imaginary axis. So we could represent this point, CR units along the horizontal axis, and then CI units along the vertical axis, the imaginary axis. And then this is the complex number C on that plane. Okay. Again, that's one representation. There's a couple of other representations. In a lot of our work, it's actually the exponential representation or the polar representation that is more convenient. So, I could tell you how to find C by, walk due east CR units and then walk north CI units, right? That would be one way to find the point. The other way is say, okay, you're looking due east, turn counterclockwise 30 degrees and walk, 10 units. That would also be another way. If I gave you this angle, and then this distance, which I'm going to call A, that would be another way to locate that point, right? Now again, there has to be a convention with the angle. Should we measure it from north? Should it be measured clockwise, counterclockwise? The convention that we use is it's measured from the real axis, and it's positive going counterclockwise. Okay? So this would be like, it looks like approximately a positive 30-degree angle. This would be a -45. This would be a -90. Of course, 270 is the same as, plus 270 is the same as -90. By convention, we try to, you don't have to, it's a convention. We try to give our angles so that they're between -180 and +180. Okay? And then that covers the whole plane. So this gives us another representation. It's called the exponential representation. I'm just going to assume that you trust this e to the j psi for a bit. We'll talk a little bit more about that. What's that exponential doing in there? And then there's another representation that's directly related to the exponential representation. It's called the polar representation. The exponential representation is really convenient for multiplying complex numbers. The polar representation you often find on some calculators, on a lot of several of the TI calculators have that. The TI-83 does not. You have to enter, if you're going to use the magnitude angle form, you have to use the exponential representation on the TI-83. And that's one of the problems with it. Okay, so some of the notation you'll see. This is a script RE. The real part of C then is CR. The imaginary part of C is what we call CI. The imaginary part of C is just CI. It's not JCI. Okay, so And then the magnitude of C, or the absolute value of C, or the amplitude of C, that's what we call A. And then the angle of C, sometimes it's written as the argument of C. Sometimes you'll see this notation. That's this counterclockwise angle from the real axis. Now you can use just, this is a right triangle. So you can use trigonometry and the Pythagorean Theorem to convert back and forth between the representations pretty easily, just a little knowledge of trigonometry. For example, how would you calculate A from CR and CI? Square root of the sum of the squares, right? So that's the Pythagorean Theorem, square root of CR squared plus CI squared. It's the square root of this length and this length. Again, this length is CI, it's not JCI. A common mistake students will make is for the imaginary part, they put like J3 here. If you square J, you get minus, and that gives you an incorrect result. Okay, so if it's 4 plus J3, this is 4 squared plus 3 squared, not 4 squared plus J3 squared. A is, all of these are real numbers, right? C is complex, but CR, CI, A, and Psi are all real numbers. How would you get psi? How's it related to CR and CI? It's the tangent, inverse tangent. The tangent of psi would be the opposite over the adjacent, CI over CR. So psi is going to be the inverse tangent of the imaginary part over the real part. Okay. You could, once you've got A, cosine of psi is also CR over A. You could use that to use an inverse cosine. But if you want to go from the rectangular representation to this will get you either the polar representation or the exponential representation. Another thing I'll caution you about is, the angles may be expressed in either radians or degrees, so be careful with that. Okay. Typically, electrical engineering, we use degrees to represent our phase shifts. Okay. And so even though omega t, if omega is in radians per second, which it is, multiplied by t, this argument is in radians. And so if this is in 30 degrees, we can't actually evaluate that without converting one term, either this from degrees to radians or this from radians to degrees. Before we can actually add those, we have to make sure they have the same units. So different calculators kind of handle that differently, so be careful with that. So what if we've got the polar or exponential representation and want to go back to find CR or CI? So we've got A in the angle. How's CR related to A in the angle? It would be cosine of the angle is CR over A. So CR would be A cosine of the angle. What's CI then? A sine of the angle. So these formulas allow us to go back and forth. If you know how to use your calculator, you never have to use these formulas, right? There's a little button on your calculator that will convert from rectangular to exponential, or rectangular to polar, or polar to rectangular. Okay, so it's nice to be able to do this for theoretical derivations, but often if we're working directly with numbers, just use your just use your calculator. So going back to this representation, we know we can write this as, I'm going to factor out the A, sine psi plus J sine of psi, where I've just expressed CR and CI in terms of the amplitude and phase angle, right? Comparing to our exponential representation, C equal A J Ci, we have e to the j psi is equal cosine psi plus j sine psi. Okay. That's called Euler's formula. Now, I didn't prove Euler's formula here because I kind of asked at the beginning for you to accept this exponential representation. Okay? But if you accept that, then you get to that equality. Okay? You actually prove it by looking at the power series expansion for the exponential and the trigonometric functions. And you can see based on the power series that that's an equality. Okay? And that's called Euler's formula. It's kind of fundamental to, if you know Euler's formula, you don't have to know any trigonometric identities. You can derive them, all of them, in just a few lines. Okay, there are a couple of different forms of Euler's formula that are handy to know. If I stick a negative sign in there, let psi be negative. Cosine of a negative angle is the same as cosine of the angle. Cosine is an even function, but sine of a negative 45 degrees is the negative sine of 45 degrees. So it's really still Euler's formula. I'm just sticking in, a negative angle. We can also solve for cosine. If I add these two formulas together, my j sine parts cancel out. So I get 2 cosine here is equal to the sum of these two exponentials. So I divide by 2, and I get this result. Is 1/2 e to the j psi plus 1/2 e to the minus j psi. So you'll also see this referred to as a form of Euler's formula. It's derived quickly from Euler's formula. Similarly, if I subtract this second line from the top line, my cosines cancel out. On the right, I'll get 2j. So I get sine of psi, I'm skipping a little algebra, is 1 over 2j e to the j psi minus 1 over 2j e to the minus j psi. Okay. So just an aside, I asked you to do a proof like this in the homework. Okay, so I've already posted the homework assignment. So in the homework in this class is due on Monday. So I've already set up Blackboard so that you can upload it. Please scan it into PDF. Don't take pictures of it. And so find an app on your phone. And I use Adobe Scan, which I think is free. Google Drive has a scanning app built in. But you can derive almost all trigonometric identities from Euler's formula. It's easy to multiply exponentials, right? Or divide exponentials. If you multiply 2 exponential terms, you just add the exponents. Okay, so this is cosine of A. This is cosine of B. So I get 1/4 I'm going to multiply these two. I'll get A. This is the first terms. Then I'll get the last terms. Then let me do the outer terms. And then finally the inner terms. Doesn't look like I've simplified much at this point, but what you want to look for when you're working for these things is anytime I have, something like e to the j theta plus e to the minus j theta, I know that's related to cosine. If I have e to the j theta minus e to the minus j theta, I know that's related to sine. So if I look at this is actually 2 cosine of a plus b, the first two terms here, right? 2 cosine of a plus b. Okay. So multiplied by the 1/4, I'm going to get the first term as 1/2 cosine of a plus b. And similarly here, I've got a sum, but with the exponent as a minus b, e to the j theta plus e to the minus j theta. And that's cosine. It's 2 cosine times 1/4 would give me 1/2 cosine of a minus b. And that's, that's one of your fundamental, and I don't know, when I took high school, it seemed like it was nothing more than high school trigonometry. It was nothing more than memorizing about 30 trig identities. Once you spend a little time with Euler's formula, realize you don't have to memorize any of that stuff. It's so easy to derive using the properties of exponentials and Euler's formula. Okay, so let's do some examples here. I'm going to ask you to find the phasors. So V of t is equal 5 cosine 200 it plus 30 degrees. Okay, so typically books will differ in representation here. Often for a phasor, it's shown as an uppercase in most texts. It's an uppercase bold type. I can't do bold on the blackboard, but you'll be able to tell it's hopefully a phasor by context. What would be the corresponding phasor here? In polar form. It's just trivia, right? So it's just 5 at 30. You could write this as 5 e to the j 30. Now again, be careful here. If there's no degree sign there, that means that then it's assumed that whatever's multiplying with the j is actually in radians. Okay. And then you could also write this as e to the j pi over 6. Right, 30 degrees is, remember 180 is pi, right? 360 is 2 pi. So 30 degrees is 1/6 of 80, or 30 degrees is 1/6 of 80 degrees. It's also 1/6 of pi radians. Or, we could write this as 5 cosine of 30 if your calculator's in degree mode, or 5 cosine pi over 6 if your calculator's in radian mode, plus j sine of 30. And that becomes 4.330 plus j 2.500. Do you have to do all of those? No. The first one is fine. If you're asked to find a phasor, these are just different representations of the same number, right? When you're adding complex numbers, at least by hand, it's most convenient to use the rectangular form to do that, because you add the real parts, add the imaginary parts. If you're doing by your calculator doesn't care. It'll just happen.
I was just gonna ask if you might find the sign for me.
I did to get the result, I just left it out of there. I left it out of there, thank you. Now here you have to be a little careful because in this conversion from sinusoidal form to phasor form, our reference sinusoid, and it's a convention, is a cosine. Okay. So here we have a sine. We have to convert the sine to a cosine. Now again, you could refer to a book of trig identities. I just mentally picture what the cosine looks like, right? This is cosine of theta. What's cosine of theta minus 90 degrees? We worked on shifts yesterday. If we subtract, which way are we shifting? Shifting to the right, okay. So cosine of theta minus 90 degrees is going to be this thing shifted to the right by 90 degrees. So 90 degrees is 1/4 of the wavelength, or the entire period. So now what's this? That's a sine, right? Now actually if we added 90, you actually get the negative sign, so be careful. Sine of theta. So I have to use that little trick first. Sine of this is actually cosine of this minus 90. Okay, 100 cosine omega 0t minus 60 degrees. So the current phasor in polar form is 100 minus 60. Is that clear? So is my microphone still working? Can you still hear that from the back? Okay. All right, and then I'm not going to bother with converting these to all the different forms. So what's the corresponding time domain expression with the phasor in that form? Well, in polar form it's simple, right? It's 12 cosine omega 0t plus 45 degrees. I didn't give you the frequency, so, and you have to know that that has to be given in order for us to actually sketch what the corresponding sinusoid is. Now that's a puzzling one. I is minus J90. That's really in rectangular form with no real part, right? Where would that point be here in the complex plane? Straight down, it would be here, 90 units down, right? How would we express that in polar form? What's the angle? Okay. This is our zero reference, right? Minus 90 or plus 270. Both of those are correct, but by convention, we try to get our angles always between minus 180 and plus 180. So the angle here is minus 90, okay, and then it's 90 units down. Okay. What would be J10? What would that be in polar form? 1090. What would be I equal 30? 30 at 0 degrees, right? That's just a real number. It's on the real axis. What about I equal minus 200?
200 negative 90.
Not negative 90.
Minus 200, not 200.
Minus 200. Just minus 200. It's on the real axis. It's 180 degrees. It's also minus 180 degrees, right? So it doesn't really matter which you use. I think the convention is always to use the plus 180. What would the corresponding polar form there be? Well, this is the same as e to the j1, right? The polar form would be 12. Now, what's this 1, though? This is where you have to be a little careful. Is that radians or degrees? There's no degree symbol, so you have to assume it's radians, okay? So 1 radian, what's the conversion between radians and degrees? Well, it's 180 degrees over pi radians. So this would actually be in degrees 180 over pi, or 12 at 57.30 degrees. So V of t is 12 cosine of omega 0 t plus 57. I'm sorry, I wrote 53, but it's 57.30 degrees. Okay, one more. Let's say I is 3 minus j4. Again, just if you punch that in on your calculator, say, give me that in polar form or exponential form. This is just 5 at an angle of minus 53.13 degrees. Okay. So the corresponding voltage is 5 cosine omega 0 t minus 53.13 degrees. Okay. So any questions about any of that? I remember being a little confused about phasors when I was a sophomore in college taking circuits. You know, and I ran into this voltage of a phasor voltage of J120. It's like, that's imaginary, you know, that can't hurt you. Okay. But a phasor of J120 corresponds to a sinusoid, what? Of amplitude 90 and a phase shift of 90, right? We looked at a minus j here somewhere, right? This is a purely imaginary number. It represents, did I write down the current for that one? Looks like I skipped it. That imaginary phasor represents a completely real sinusoidal, in this case, current or voltage, right? You know, if this were J200 volts, it would represent a sinusoidal voltage, a completely real voltage with an amplitude of 200. Okay? It's just phase shifted from our reference, but it's just as deadly as, you know, J1000 would be just as dangerous as 1000 phasor, right? They have exactly the same amplitude. They're just shifted in phase or time. Okay, so why do we use phasors? I'll just show some examples. So let's say V1 of t is 10. V1 of t is 10 cosine 200 pi t plus 30 degrees. V2 of t is 5 cosine of 200 pi t minus 60 degrees. Now I could actually add those using a whole bunch of trigonometric identities, okay, and a whole bunch of paper and algebra, and come back in 30 minutes and give you the answer. Okay. Alternatively, and this is the real value of phasors, the phasor sum is equal to the sum of the individual phasors. So V is equal to V1 plus V2, which is 10 at an angle of 30, plus 5 at an angle of minus 60. Now, I'm not going to go through doing that by hand. Again, use your calculators to do that. What you get is 11.18 at 33.435 degrees. Okay. If we convert this back into the time domain, 11.18 cosine of 200 pi t plus 3.435. Boy, you get the numbers on the board. Long summer. Now I haven't proved that this is the right result, that by adding the phasors I get the same result as if I'd added the time domain expressions. I'm not going to go through that proof. Okay, it's a long proof, but just believe me when I say that you get the same result, and it's trivial here. Okay, now why would we ever add voltages? Well, Kirchhoff's voltage law, okay, requires us to add, voltages around the loop. Okay. The voltages in a loop may have different amplitudes and phases. They're all going to have the same frequency. And so instead of trying to do this sum of all these time domain sinusoidal expressions with a bunch of trig identities, I can just add the corresponding phasors, convert back into the time domain, and I've got the right result. Okay. Makes things really simple. Now this only works if all of the sinusoids are at the same frequency. I can't add sinusoids, I can't add the corresponding phasors if they're at different frequencies. If this is 200 pi and this is 300 pi, it doesn't simplify. Okay. They don't add to give me a sinusoid at some other frequency. You can't do anything with it. It would be 10 cosine 200 plus 5 cosine 300 pi t. Okay, it doesn't simplify at all, okay, if they're at different frequencies. But, if I've got one sinusoidal source in my circuit, all of the voltages and currents in the circuit are going to be at that same frequency. And so Kirchhoff's voltage law, Kirchhoff's current law apply. So this is one reason, is it makes addition really easy, differentiation. The other reason, it also greatly simplifies differentiation. Okay. So I will go through this, derive this result. It's just a few lines. Okay, the corresponding phasor here is an exponential form is a e to the j theta. Right? If I take the derivative of this, I'll call it V2, dV1, dV2. My cosine becomes a minus sign, right? Minus omega 0 a sine omega 0 t plus theta. I pull out the omega 0 when I take the derivative. Right? Then the minus appears because the cosine becomes a sine. I want to convert V2 back to phasor form. Well, I gotta get rid of the minus sign. I can do that by actually adding 180 degrees. If you shift the sine wave or cosine wave to the right or the left by 180 degrees, you get the negative waveform. Right? If I shift it by half a period, I get that negative waveform. Now the next thing I have to do is convert my sine to a cosine. I do that, did I have it written down up here? By subtracting 90 degrees from the angle of the sine. Okay. So I get omega 0 A cosine omega 0 t plus theta plus 180 minus 90 degrees. Shifting a cosine to the right by 90 degrees gives me the sine, or omega 0 A cosine omega 0 t plus theta plus 90 degrees. So this would be the corresponding time domain expression for the derivative, going through all of that work. The corresponding phasor is omega 0 A e to the j theta plus 90 degrees. Okay. I can write that as omega 0 e to the j 90 degrees times A e to the j theta. Right. The reason I do that is because that's V1. I can separate out V1. So V2 is omega 0 e to the j 90 degrees times V1. Now what's e to the j 90 degrees that has a length of 1, but what's e to the j 90 degrees in rectangular form? All the e to the j thetas have a length of 1, so they're on what we call the unit circle. But e to the j 90 would be what? Straight up. So it would be what in rectangular form? It's imaginary, has a length of 1. E to the j 90 degrees is just another way to write j. Right. So V2 in this case is j omega 0 times V1. So in order to differentiate in the phasor domain, it's trivial when I'm dealing with sinusoids. I just multiply by j omega 0. The omega 0 changes the amplitude I get from the differentiation. And then the j is a 90-degree phase shift that I also get from the differentiation. Okay, just really quickly. Okay. We know, for example, V is equal to L di dt. It's the fundamental voltage current relationship for an inductor. You know, for resistor, V is equal to IR. For an inductor, V is equal to L di dt. Okay, that's the time domain expression. So the corresponding phasor expression would be, I've got to multiply by L, but in the phasor domain, how do I get the derivative of I? I multiply my I phasor by j omega. That's all I do. So in the phasor domain, to find the voltage across the inductor, I just multiply the current by j omega and L. Or I can write this a little differently. As to get the voltage across an inductor, I multiply the current by j omega L. Now this looks a lot like Ohm's law, right? It looks like V is equal to Ri. So we make that identification. We call this thing, this j omega L, we call that an impedance. So that we get this in the phasor domain, we get this expression that looks like Ohm's law. Now, you'd have to go back to your circuits 1 to verify this, but all of those circuit analysis methods you used in circuit 1, mesh analysis, nodal analysis, superposition, those were derived, series impedances, parallel impedances, those were derived from 3 fundamental relationships: Ohm's law, Kirchhoff's voltage law, Kirchhoff's current law. You didn't actually learn any other fundamentals other than those 3. You learned a bunch of different circuit analysis techniques that all were derived from those 3 fundamentals. Okay. Now in the phasor domain, we know that adding voltages in the time domain is equivalent to adding phasors. So we've got a Kirchhoff's voltage law in the phasor domain. Same is true for currents, sinusoidal currents. We add the corresponding currents. And now we've got something that looks like Ohm's law if we talk about impedances instead of resistances that apply. Okay. So now in the phasor domain, instead of working with these sinusoidal time domain functions, we can work directly with our phasor voltages and currents. We can work with impedances and still use all of those basic circuit analysis techniques. Except everything's a complex number now instead of a real number like a real resistance. And then I think you guys remember the impedance of a resistor is R. The impedance of an inductor is j omega L. The impedance of a capacitor is 1 over j omega C. Okay. And I can add impedances, in series. They just add. Impedances are also complex numbers, right? But be a little careful with your terminology. This kind of tells engineers from non-engineers. Not all complex numbers are phasors. Impedances are complex numbers. Phasors are complex numbers. Phasors are specifically representations of voltages and currents as complex numbers. These impedances, they're complex numbers, but they don't represent voltages and currents. Okay, have a good weekend. No, I'll see most of you again later today. A couple times, maybe. Sorry. All right, so I shut down my recording here.